Welcome to Ask and Learn.
So in this case, we have a dairy plant that's pasteurizing milk. The milk is initially at 4 degrees C, and we need to get the temperature up to 72 degrees C to pasteurize it, and then we cool it back down to 4 degrees C. We have a volumetric flow rate of milk that's passing through this pasteurization process of 0.012 cubic meters per second. Let's see here. Then we have, we'll take the density of milk to be about roughly the density of water. And the heat capacity of milk we can look up. And so we can get the mass flow rate, and that's about 12 kilograms per second then. Now, to heat this milk up, we have a boiler that then, transfers heat into the milk. And so what we're doing here is this is kind of a I'm not sure exactly how to really draw this picture. We stick a regenerator in here to try to recover some of the as the milk cools. Obviously, we could recover some of that work. And in fact, I'm not sure exactly what kind of regenerator this is. But I think it is probably just trying to capture the thermal energy as the milk cools and cycle it back. I'm not sure. They don't really say it's a heat engine, so I think it's really just a kind of a thermal energy capturing device. So what we're doing, we're told that the boiler has a efficiency of 82%. And let's see here, what was and then the pasteurized milk is cooled by water that is it's cooled from here to here by water that is 18 degrees C. I guess they didn't actually say that the pasteurized milk got down to this temperature, but that the cold water it's cooled by is at this temperature. So I'm assuming that it gets close to this temperature, and then it's refrigerated back to 4 degrees C. So we have then the case where, and this is done continuously, 24 hours a day, 365 days a year. I guess they get February 29th off every 4 years. Let's see, bad joke. So this regenerator they stick in there also has an efficiency of 82%. Now we're told that energy, so the natural gas that's firing this boiler or heating this boiler, is $1.30 per therm, and a therm is 105,500 kilojoules. Right? So initially, we have just basically this heat from the jet going. We have something going into the boiler. Its efficiency, the heat coming in from the natural gas burning. We have the boiler. It's transferring heat out to the milk. And then, I'm not sure where the regenerator goes in this picture, but anyway, that heat then winds up into the regenerator, which then passes it back to the boiler, basically in giving it to basically help keep the boiler temperature up, or the water and the temperature in the boiler up. So we know it's a steady flow process, right? So that means that the heat transfer in to the milk is basically the change in enthalpy, the rate of change of enthalpy in the milk. Okay, or yeah, the rate of change of entropy of the milk. So we're getting it, heated up. And so this is from 1 to 2. This is during this heat process here. And so again, we're going to assume constant heat capacity. And again, we look that up. And we wind up with 3,090 kilowatts. So then again, we have, we're asking about basically how much money we're going to save, which is the first big question. Well, first, how much fuel we're saved, then how much money we're saved, and then we're looking for how much exergy is destroyed during the exergy destroyed due to the reduction in heat transfer to the water or in the water. Okay. So now we're going to look at the total heat transfer. Let's see here. The heat transfer that comes out of the regeneration operation is 82% of what went into the milk. Okay, so that we got 2,540 kilowatts. Now, that is actually the the energy that we saved. Because it is what we pulled back out of the milk and then pumped back in to the boiler. And so that's, if we convert it to therms, we have 0.02930 therms per second. And then we convert that to years, we have 924,500 therms per year. And then we can multiply it by the cost per therm, and we get a savings of, I guess I should put per year into here. We get a savings of about $1.2 million per year. So again, this regenerator, probably expensive, but it will be probably a good investment, as it's going to save us quite a bit of money every year. So probably a very worthwhile investment. Now, let's see here. We're asked to figure out the rate of entropy generation during this process. So we're gonna basically look at the entropy generation by looking at the system and the extended surroundings. All right. So again, we have so this is it's steady flow process. So so we're looking at the regenerator and kind of like all of the the surroundings of the regenerator. I think I said the whole thing, but we're just basically looking at the exergy that was destroyed in the regeneration process, but we're doing an extended control volume, not just close to the regenerator. So again, the rate of entropy generated in this is the rate of entropy flowing out minus the rate of entropy flowing in to this extended control volume. And that is basically this the exergy that was saved in the end, because we have again, then we have this cooling water here. And so, as this cooling water, we're basically, I think what the process is we're going to try to extract some heat out of this cooling water, probably, in the end, because this cooling water is going to get, its temperature is going to go up unless it's, a huge, like a lake or something. So again, I'm not sure exactly how this regeneration process is working, but we know that if we extend this out, we're going to be at this, 18 degrees C temperature. And so that's where the heat transfer out of here is going to be, right? Let's see here. We then have the and again, I'm not sure. I don't know if I've drawn this picture what is like what they had in mind, because here we're showing heat transfer going into the regenerator. I'm not sure if that's really how what they're looking at for um, what they mean by how the regenerator is working, that heat is flowing into it and then flowing back out. I'm not sure that this is actually accurate here, because um, in anyway, what I solved for here is, well, I just assumed that there was this heat transfer out, which is the heat transfer saved, that's actually going um, to the causing the causing the entropy increase. Um, so anyway, so we have the entropy saved here. Again, I'm trying to work towards the answers that they have on that they gave us, and so sometimes, yeah, I have to do a little bit of back calculating to figure out how they got how they got what they got, and I'm assuming that if I use the rate of rate of thermal energy saved, I can get what they got. But I'm not sure exactly how this regenerator was supposed to be analyzed. Anyway, that winds up being 8.715 kilojoules, kilowatts per Kelvin. And then we can convert that to uh, years. So it's kilojoules per second per Kelvin. And so we can convert that to kilojoules per Kelvin per year. And we get this. And so then we multiply by the surrounding temperature, um, which we're assuming is 18 degrees C again. And we get that you get about eight times 10 to the 10th kilojoules per year of exergy destroyed in this regenerator. Okay, so again, we don't get everything back, obviously. We do save some, but we also destroy some exergy in the process in this regenerator. Anyway, it's a little bit of a weird problem because I didn't initially get this answer that they got, and I had to realize that they used Q dot saved here, which means that maybe this picture isn't quite accurate. Um, Again, it's not clear where this regenerator is actually where it's placed. Basically, they say they installs a regenerator. Okay, so I'm not exactly sure where the regenerator is getting its energy. It might be something like we have, um, say here we have, say just let's say we have milk. Okay, maybe we can look at it like this. So we say we have milk flowing. We have heat from the boiler going in, then heat coming out later on because, but as it's cooled. And so then say we have the regenerator here. So here's the boiler. And then the regenerator is somehow transferring heat back to the boiler to help heat the milk out the earlier stage. But then you still have this kind of this. Well, I guess okay. Here's what I suspect that we're looking at then. What they're saying is that Okay, let's take our control volume as something big here, like this. So this becomes internal heat transfer. And so this is just the external heat transfer. Okay, if we take, so basically we're looking at this as an internal heat transfer that didn't go to the surroundings, but came from the milk into the regenerator. So now if we can draw this control volume here, then we have the uh, uh, heat transfer. The only heat transfer across this boundary is then this heat transfer, that heat that was saved. So that was probably what the situation is more accurately depicted than this one up here that I initially drew. So that one's probably not what they really had in mind. Probably something more like this.